Okay, so Bio's been talking about horizontal variation in currents, and I suppose one of her messages is sort of, how am I supposed to live without you? And I will take that one step forward and say, how am I supposed to live without the vertical derivative of you? But we're going to leave the leave the real world for a little while, because I've been in my delinquent youth working a lot with theory and trying to take it into the real world lately. So I'm going to throw out a lot of results and things that we have made, and the big thing is for you to give feedback on when is this of importance, when is it of interest in the real world. Clearly some of it is interesting sometimes, and clearly sometimes it isn't. So anyway, this is supposed to be a hybrid summer school conference, and so it's a bit funny to give a pedagogical talk when half the audience knows this better than I do. So it will be a sort of, I'll start a bit pedagogical, and then it'll turn into focusing on my thing. So the contents, something old, something new, something borrowed, and then, as we can see on the photo, water is blue. So, and also, Antinu insists I keep this bottom, which is also blue. So that's okay. Right, so I'll start with vertical shear. So here is the setting. So the currents vary, and I'm going to focus on situations where the currents only vary vertically, which is to say that the horizontal variations are slow on the scale of a wavelength. The currents can vary directionally as well, but I don't think I'll be having many examples of that. I'll try to give some basic theory and concepts first, and some take-home messages that may not have been emphasized so much in the literature. And then I'll run through some real-life cases, or at least some cases where it might matter, but of course hand-picked, because we pick locations where we expect to find order 1 results. And then I'll go on to talk about turbulence, which is something I've been working on more lately, because waves and currents have a distinctly turbulent relationship, and we'll see that turbulence, even on the scale of a wavelength, comes into play. So waves on vertical shear. So we assume horizontally uniform conditions for now. I will focus on, let's say, realistic shear profiles. A lot of the theory is developed where u is proportional to the depth coordinate, so it's purely linear in the vertical direction. This particular case is a nice model in a way, but it's got some weird features as well, very peculiar features. So I'll be looking into more realistic profiles. Oh, okay. Well, I think it's fair to say that linear theory has become relatively well developed. But looking at 3D wave phenomena surprisingly recently, even though the machinery has been in place for, well, nigh on 100 years. Weakly nonlinear theory with the realistic shear profiles is, well, the machinery is basically in place, but there are lots of new insights coming even now. And as for fully nonlinear wave shear current interactions, I would say there is still limited understanding, and it's not entirely trivial to even know what we're talking about, because well, fundamentally, well, in these in weakly nonlinear theory, we like to say, well, it's flow, it's current plus waves, but of course this is in a way fiction. What we have is flow with initial and boundary conditions, and when it's fully nonlinear, it's not necessarily trivial to say what you're talking about. So perhaps waves with vorticity, where you define the inlet conditions. Anyway, yeah, so when the vertical shear, well, hello. When when u varies with depth, it should be z, yeah, u derived as z, then the dispersion is anisotropic in every system of reference. This is different from where there is no depth dependence. Then you can go to the local system of reference that follows the surface, and then the surface can be transformed out of the equations with a Galilean transformation. You can't do that. So the system is fundamentally anisotropic. This is a lab experiment that we did a few years ago. Here, in both cases, the surface is stationary, but in one case here we have a strong subsurface current, and you see that the ring waves would just puff some air onto the surface, and you see the ring waves become anisotropic, and it conforms very well with theory, so that was gratifying. We also ran a ship right across, a 10 centimeter long ship right across the current, and you see these asymmetric ship waves. So it's a nice little example. So the dispersion relation, as we're sort of used to it, has the dispersion relation we know and love without current, and then there is a Doppler shift type of construction. However, when there is variation in current, then this effective Doppler shift depends crucially on the wave number. So, which means that you can do like Luc Lenard showed. Well, he didn't actually show this time, but he normally shows it. You can infer the current from looking at the wave surface only, looking at the 3D spectrum, and you see that if you make a prediction just from the surface current, you can get, in this case, this orange line, whereas in fact you observe something that lies along another line, and you can infer from that not just the surface current, but also actually something about the depth dependence. It's quite neat. There is an essential point that's been made by Jim Kirby's group in particular, that if you're going to look at the group velocity here, this thing looks like a standard Doppler shift, and it has sometimes been interpreted as that. So you calculate that, and you just add it to the group velocity. Well, you can't do that, because it depends on k. So you need to take the derivative of that as well. So that point was pointed out by Hashemi and Kirby. And it does make a difference. So as they say, it's been suggested for use in wave models by a number of authors. They don't say who that is. But it doesn't matter anyway. But it's a point well worth taking into account. So very much used approximation for the dispersion relation, or for this Doppler shift, is Stewart and Joy, 1974. That's the deep water version. There are shallow or finite depth extensions that we also know well, Scope and Kirby and Shen. And what it shows you, this, as I say, it normally works. I'll tell you something about the criterion for it to work, but it normally does work. And what it shows in particular is this factor, which it looks a bit like what we know for the Stokes drift, but it's not sort of the same thing. But it means that U only matters down to a depth of perhaps a quarter of a wavelength. So it's what happens near the surface, but then of course waves can be pretty long. So different wavelengths see very different currents. That is something to bear in mind. But there's no such thing as strong shear in itself. It's strong shear as seen by a wave of a certain wavelength. So we derived a few years ago, looked at the criteria for using Stewart and Joy, and came up with this non-dimensional parameter for a wave of wavelength k, which is sort of the depth-dependent gradient of U, and it has the shape of a Froude number, and Stewart and Joy or Scope, there is a finite depth version of the same thing with some Singe and Koch functions in it, but when this parameter is small, then Stewart and Joy is basically good. When it's order 1, you need to do something a bit. There's another model you can use that's equally simple. Student joy can in fact be written. Just do a partial integration of the student joy expression, and you can write it like this. So actually, you here see that this is the correction due to the vertical shear. So that's nice. You got a criterion that you can easily check. And what it doesn't say, what it says here is nearly always good for oceanic conditions. So everyone who's been using the student joy expressions for many years, that's probably no problem. But there are cases like in river plumes, things like that, where you might want to check a bit more carefully. Another point that's well worth noticing is the use of potential theory that is very common. Now, it's no surprise, I suppose, but it needed to be pointed out at some point that in an Eulerian formulation, surface waves are basically always rotational. There is basically only one very special case where you can consistently use potential theory. But it's really nothing dramatic or strange about it. All it is here is a wave traveling at a slight angle, and you look at the vortex lines in the flow, and all it is really is that the wave motion is, according to Helmholtz theorems, it's just grabbing the vortex lines and shifting them like this in a Lagrangian way of thinking about it. It's pretty unsurprising, but Constantin, as a mathematician, proved his theorem that if vorticity is constant, all waves must propagate exactly aligned with the current, which led to some misunderstanding that if there is vertical shear, then all the waves must propagate along the current, which is of course absolutely not the case. It cannot be. I mean, throw a stone in the river, and clearly there's a ring wave. It's not a plane wave. So it caused some confusions, although the statement is perfectly true, but the assumption behind it isn't what we normally see. Anyway, so that's the thing. And if you go to second order, we know I'm not going to talk a lot about it, but then you get the Stokes drift interacting with the background vorticity. And just to mention that, there is also an expression for the wave action derived by Voronovich a long time ago. N and F here are basically equivalents of wave action expressions, and there is something going on here. Anyway, so there are some So there are some simplifications derived where you can have them in. I'll go through some examples of cases where the vertical shear does seem to make a difference. The standard testing ground for all of this is so often the mouth of the Columbia River for a couple of reasons. First, there is a very strongly sheared current there, which is nice because we can cherry pick it and say, well, if it we say, oh look, this is important because we have real data. But of course, this is a hand-picked location. But there is heavy ship traffic, so people do care about it. It's and there is Zoom seems to be having some trouble here. Yeah. Anyway, and there's excellent measured data, both the waves and the currents. So it's a good place where there's a freshwater plume floating on top of the saltwater, creating a strong surface jet. And we see that, well, here it's modified, so the surface velocity is 0, but the currents are up to a couple of meters per second. So it's good for this purpose. One thing that's perhaps not so interesting for this audience, but it's a nice little illustration of why perhaps some people might be interested in it when they look at the forecasts. The wave-making resistance on ships. So ships, boats, make waves, obviously. These waves have energy, which they take off with, and so that's a very important source of drag on ships. And here you see it, if the ship is going at the same fruit number, these tugboats that operate in this area typically have fruit numbers in this range, 0.3, 0.4, and relative to the surface, there's this, and you see that the wave-making resistance can vary very drastically, whether they go upstream or downstream. There's also a sideways force on the ship because the wake is asymmetric. Anyway, another thing is that here is another thing is that the velocity field beneath the surface can be quite different. Here is actually, this is an exponential shear profile. And even though here is just an initial perturbation that we allow to just go out, and after a while the surface really doesn't look very different. It's, well, not drastically different, but the velocity field, this is the velocity field magnitude. You see that here we've subtracted off the mean velocity, looking just at the wave-induced one, and you see it looks very different. So what goes on underneath the surface can be very different, even though the surface isn't radically different. This is very exaggerated, but here I'm looking at waves that are dispersively focusing to a Gaussian wave around here. And you will see that here there is some extremely strong shear here, just that you see the effects, but it's the same in the Columbia River profile. So if you look at the envelope of this focusing wave, it's really very similar. This is without shear, and this is going against the current. So what you have is assisting shear upstream, let's say. And if you look at the appearance, the envelope is basically the same, but this thing has a very slow evolution, whereas this thing looks quite volatile. And you will see that the velocities are much higher here than they are here, the wave-induced ones. This is exaggerated, of course, but it matters a lot to how do these waves appear if you approach them with a ship, for example. In the Columbia River, we used the actual measured spectrum by Zippel and Thomson, thinking, okay, what if these waves appear on top of each other? So kind of rogue wave scenario. And the actual currents, and we see that the velocity of the peak of the wave is reduced to 70% or increased to 140%, depending on whether it's going upstream or downstream. So it's not necessarily small. I'll mention this paper by Seth Zippel and Jim Thompson. I was hoping to meet them here, but unfortunately they're not here. So they looked at the Columbia River mouth, and they looked at the wave breaking rate, and tested some models, the Shaolin Kirby, Banner et al. And they only got it to match pretty well if they took into account the vertical shape of the current. Otherwise, and only then did they get this the bulk steepness breaking beneath 0.4, which they wanted. Yeah. Then I'll look into statistics that Zipo Zheng, who just finished his PhD, did. So the second order theory was derived, where you take the linear theory, you just plug it back in, you get some ugly integrals, convolutions and all that. Anyway, and he ran some simulations with lots and lots of waves. So we consider only the 2D case of against or along the current, so it's not, this has some limitations, as Victor Schrerer has pointed out to us. So don't take the actual numbers too seriously. But what we see here is that this is the exceedance probability, the rogue wave limit on crest height. And what we find here is that the rogue wave probability is increased quite a bit or decreased even more, depending on whether you're upstream or downstream. So it does seem to matter to that. So this, as I said, this study had some limitations, but because in particular there are triad resonances with critical layers and things that aren't taken into account. But nevertheless, then there's with the modulational instability, which you also like. or the other way around, often considered a main culprit or suspect for rogue wave generation. Now, this is what you often see in the lab. So this is from our lab. You just set your wave maker to constant frequency, and a few meters down the road, the waves start to become groupy if the steepness is high enough. So that's this is well known. Now, this experiment was done for a paper with testing Nick Piso's Lagrangian theory, and quite according to oh, I'm going the wrong way, that's why. And so it's been shown before. I don't know, probably the references are in our yeah, it's been shown theoretically and experimentally before that if you have assisting shear, this can stabilize and remove the modulational instability. And that's the same time actually as the crest speed is reduced, as the velocity at the crest. So this was shown theoretically a long time ago for the linear shear case, and then for arbitrary shear. These are some papers. Nick Piso's the real expert on this, as in he's the real expert on many things. So, but we did this experiment, and I'll show you the lab a little bit later. I presented it at WISE before, but not this one. This experiment is slightly buried inside Nick's paper, but it's quite a neat little experiment done by the postdoc Olav. So we were able to create an Eulerian mean flow that is approximately the same but opposite to the Stokes drift. And then, I guess it's the closest that anyone's come to making a Gerstner wave. And then you see the modulational stability just vanishes. So that was gratifying. And yeah, it was a nice little demonstration. Now there's a recent paper, very recent paper, that argues that actually Langmuir circulation and modulational instability should be considered together. They are considered two separate instabilities. These are famous pictures. But the CL2 mechanism by Craig and Leibovich says that the system is unstable to Langmuir circulations if the slope of the mean profile times the slope of the Stokes drift profile, if they have the same sign, like in this picture. Well, that's also the most unstable case for the modulational instability. So Yan Li and Amin Shabjob published this paper just a month ago, maybe, that they made a combined stability criterion. So that was quite neat. Anyway, here's a sort of summary-ish. For opposing shear and assisting shear, which you could call downstream and upstream. So what I mean is here that the shear sort of helps the wave along because the current decreases with depth. Well, so the opposing shear case, the downstream, is the most unstable to CL2, or it is unstable to CL2. It is the most unstable to modulational. It is often stable to modulational instability. It has a higher versus a lower rogue wave probability. So on the whole, it's a more volatile system. It's got higher steepness for the same sort of, well, I should say higher steepness and enhanced crest speed compared to what you would predict if you used the surface current. However, so this looks like this is a much more dangerous situation. Well, it might be, but very often, if you see, so Bia's significant wave height varies with tides, it's basically also the situation where you have calmer seas. So perhaps it's not so bad. but this is some sort of summary. Anyway, I'll be quickly also looking at turbulence. So, as we know, well, one man's turbulence is another man's slowly varying background current. Again, so I should say one woman's turbulence is another man's slowly varying background current. So, so the mesoscale and sub-mesoscale turbulence for me is pretty slowly varying, but turbulence, the turbulent cascade in the ocean varies over 8 orders of magnitude. So from, well, 100 kilometers to a centimeter or less. And there's a turbulent cascade, presumably continuous along all these scales. And this is where the dissipation, turbulent dissipation happens. So waves can make turbulence via Langmuir and braking, for example, but they also interact with pre-existing turbulence. And I'm going to focus on the latter. So there are basically two ways that we consider. One is that turbulence scatters waves. So the waves encountering turbulence are scattered. And the other is that sub-wavelength energy transfer to waves, so that the waves passing over turbulence stretches the turbulence, giving off energy to it. And this is another sink of energy, actually, of waves. Can't really remember why I put this wave spectrum in. It's one you know very well. But, but well, whatever we have done, we're very much in this regime because we're in a lab. But then a number of observations of as well. And I think it's very interesting to see how do these things scale up or down. Anyway, there are basically 3 regimes, and for theory, this is where Bia is the true expert. For when the turbulence scales are large compared to a wavelength, you've got some theory frameworks, some geometric optics, that kind of thing, WKB theory. The intermediate regime, where there is no scale separation, is the more tricky one. And here there is relatively sparse theory, and it's also quite heavy and tricky to use in practice. At least we found it so. And in the other way, on the other scale, when you assume the turbulence is small, then you got some other theories, and one is by Ardhuin Jenkins, 2006, using GLM. The other famous one by Teixeira and Belcher. Anyway, we've been looking into quite a lot this in-between case. So we in the ocean, as you see, the turbulence exists over all the scales. So to assume scale separation is perhaps a little dubious, although sometimes you have to. Now, there's a nice recent review by Savelli Verbal. I'm not going to go into models yet, because half the room knows it much better than I do. But I should say, I think that the energy cascade is now, correct me if I'm wrong, but I don't think this is perfectly understood. Various authors by various means have derived this equation. So if you look at you take the Navier-Stokes equations, you do some kind of averaging over waves and or turbulence. You find here that the change in turbulent kinetic energy as, well, some other terms, and then it scales with an interaction between the Stokes drift and the pre-existing turbulence, in particular the Stokes, the Reynolds stress that's cross between horizontal and vertical. And the Stokes drift, therefore, this is precisely the term you have, that there's another term where this is instead the mean flow. So Stokes drift produces turbulent kinetic energy as though it were an Eulerian current, which is something that boggles my mind, but that's what that's what comes out of the equations. But of course, if it's a source of turbulent kinetic energy, then it's also a sink of wave energy. So this is something that has been pointed out. I don't know to what extent it's been implemented in models, but but it is a point. But also note that there is no information here about the scales, really. That's all in what your averaging operation is. So at what scales can you go ahead and use this? Well, but it does depend closely on pre-existing turbulence. Now, right. So what I've been also interested in is that how do you actually do this averaging in a consistent way? Because there isn't really a... One thing is you take your theory and you assume monochromatic waves. Well, that's fine. Then you can just average over the face and the waves are gone. Excellent. But you don't have monochromatic waves. You have a broad spectrum of waves. You also don't have scale separations, possibly in time, but certainly not in space. The scales are the same. Can you really go ahead and write things like this? What exactly does this mean? This is... maybe someone in the audience has a very clear picture of this, and we can discuss. But triple decomposition, Daniel Ruth had said some very clever things about that. That's normally always at the bottom of what we do. Again, it's not really what happens in reality, right? It's everything's a mishmash. So I'm beginning slowly to believe that this isn't really, in reality, a unique operation. You rather have to say, you describe exactly what you did, and then analyze the strengths and weaknesses on that. So, as I say, you know, it ain't easy. This looks very much like what Daniel Ruth showed. So there's a poster by Priyanka on this. We've been testing various ways. So here it's a bit hard to see here because the wave motion is has a lot more energy. This is from our lab. The waves propagating upstream, turbulence generated propagating downstream, and we're trying to figure out the turbulence statistics. It's not so easy because you really need to remove all the waves because the waves are a lot more energetic. You remove 90% of the wave energy, you still make a big mistake. So this is very much ongoing work, but here we're having some success for proper orthogonal decomposition, a numerical decomposition method where we have basically the waves plus the turbulence. And Daniel also showed some nice coordinate transformations, which we're also trying to employ. But it is quite, it's not easy. But the first thing we did was to simply avoid the problem, to say, well, we consider not the energy, but the vorticity. And say, well, the streamwise vorticity, that's sort of perpendicular to the waves and along the current, surely we can basically say that's turbulence, not waves. And then we avoid the whole separation problem by considering waves before and after a wave group. And this is the mechanism, a nice little cartoon from Teixeira and Belcher. So here you've got a vertical vortex going around this sort of bathtub thing you can imagine. And then here comes the Stokes drift, and it grabs the vortex and it pulls it over and it stretches it and it becomes more energetic, and you also really boost the streamwise vorticity. So we decided to try and measure the streamwise vorticity. I made actually these guys. We have a little dungeon lab that we call it. It's in a deep, dark cellar. And just because I wanted an illustration for a grant application, really, we just said, okay, let's do some kitchen sink science. So there's a recirculating current, a strong vertical shear. Upstream, there's a PhD student, Zibor, with a heat gun. Downstream, with a handheld thermal camera, Olav. And then now you see to the left, it's without without any waves. You see there is some streakiness in the boundary layer, which you always have. The bright is the hot areas of this high skin temperature. The low is where the bulk water comes up. And then you see now we've got some waves coming in, and you can see sort of qualitatively what the wave does. It makes these streaks a lot more pronounced. I think it's a nice little visual illustration of the kind of phenomenon. Anyway, we've got this nice little lab that we like to play with. There we go. Yeah. So this is how we condition the flow. There's an active grid on the inlet where we can control the shear profile and the turbulence, looking at different turbulence levels. There's waves propagating upstream, so they're sort of moving on a treadmill, so they propagate a lot further than the 11 meters that the wave is. This isn't what the wavelength maker looks like today, but it's got wedges instead, but it's basically how it works. We take some streamwise PIV images, not time resolved, and then we look at the wave group. We compare 3 times. One is long before the wave comes, one is just as the wave group comes in, and one is just as the wave group is leaving. And we see the change in mean square vorticity in the streamwise direction is huge, basically. So the waves really do change the turbulence. So that was nice. So here's something that Amélie is working on. It's just data that we've got that we're eager to try and get something out of. Simultaneous PIV and PTV, that's particle tracking velocimetry. So here we're tracking the particles to see the Lagrangian flow as opposed to the Eulerian. It's not so easy to see, but it's quite nice. It's Amélie's paper. Also, extremely quickly, angular diffusion. We looked at the angular so here's where we make the waves that propagate upstream. Then as it propagates on top of turbulence, the angular spectrum, starting out quite narrow, becomes broader because of scattering. And now we look at the diffusion. And what turns out to be the case is that it doesn't really matter so much how intense the turbulence is. What matters is how big the structures are. So we see we get a lot higher thermal diffusion for the turbulence that is actually what kind of people put chairs? Anyway, yeah. So it's really the scale of the turbulence, and that was surprising to us. Here you see the highest intensity. It's a lot less scattered, and the turbulence is quite a lot higher. And actually, we took this expression. This is from Smith and Janssen, and Bia has, with Bia and Young, have derived something similar. This is derived assuming the turbulence is a lot bigger than the waves, so that you can use geometrical optic. This has no right to work. This is absolutely not satisfied. And yet it does work pretty well. Why? Well, things are ongoing, but does it mean that for the wave spectrum angular distribution that perhaps the small scale turbulence doesn't really matter so much? Who knows? Maybe it's good news for modeling that you don't need the small scales for that. Open question, I think, at least for me. And then this is the brand new result. I'm not sure if we should really show it, but as a kind of teaser, a few of us. So in this experiment that I described, we got this wave group, and in that data, which isn't in the paper, we just noticed that when we look at the Eulerian current just after the wave group versus before, it's different. So the waves have changed the mean flow. And we spent a couple of years scratching our heads what this can be, and it's very consistent all the way through. So we went back to some earlier data where instead of groups we used continuous waves and found exactly the same thing there, except it was much better behaved. Here we just took the average of its 2,000 images taken over a period of 40 minutes. So it's relatively well well converged statistically, I should really have the standard deviation of things. But so now, different from the wave groups, these things no longer really depend so much on the turbulence that we send in. It seems to have reached some kind of saturation level. Now, so we went through speaking to various people, also at WISE, both in Brest and Princeton. So it is definitely not the Eulerian return flow that we know happens because it's very concentrated near the surface. It's also not the what's called the viscous surface flow, which is extremely near the surface. So we're not even measuring close enough to the surface to see that. It's also similar but opposite to the Stokes drift. Here, so because it's just 2 days ago, I didn't have time to plot it. I didn't actually have this data on my computer, so I couldn't plot them at the same time. But this is the Stokes drift profile that you accept. It's minus the Stokes drift profile, the opposite. And you see basically that they match very, very closely near the surface, but further down they don't. So this we find is quite striking. So what is the theory for the mechanism at play? Well, it's not something that we're the first to think of, and we're working with well, a number of people, but also Miguel Teixeira for rapid distortion theory. Anyway, this is basically the mechanism, we believe, because the Reynolds stress, if you take the Navier-Stokes equations, you average them, the Reynolds stress is changed by Stokes drift acting on the stringwise Reynolds stress, which in turn, if you take the RANS, the Reynolds average Navier-Stokes equation, in terms can drive a mean flow. So the mean flow, the turbulence doesn't like to be like to have gradients, basically. It wants to be uniform. And so when it isn't, it can generate a mean flow that tries to stabilize this. It is not an injection of momentum, most likely. The momentum should average to 0 overall, but these are early days in the theory. In fact, this has been predicted in a theory paper by Brodie Pearson, which hasn't really been paid much attention to, at least according to the citation history. But I think we have to pick this out and really go through it carefully. So very much early days on this, but I think it's quite significant result potentially. Anyway, conclusions. There are lots of stuff going on, but when is this important? Does it matter? Is something. So now we've got a bit less than half an hour. So Bia, do you want to share this last thing? Yeah, maybe some very quick questions.